Welcome to the deep dive. Today, we're diving right into the heart of your computer, how its parts talk to each other, specifically the physical layer of PCI Express, Gen 1 and Gen 2.
Yeah, the real nuts and bolts. This is the stuff that makes your graphics card zip, your NVMe drive fly. It's foundational.
Exactly. And we've been digging into some detailed articles on this early PCIe logic. So our mission today,
To really pull apart how data physically moved back then, look at the clever engineering that made high speed possible and kind of set the stage for everything since.
right, we want to get the core concepts clear without getting totally lost in the weeds. So let's start basic. What is PCIe, fundamentally?
Okay, so PCIe, Peripheral Component Interconnect Express, it's essentially a high-speed serial way for computer components to chat. It came about spearheaded by the PCI SIG to replace older parallel buses like PCI and PCIX.
The parallel ones. I remember those wide ribbon cables. What was the big problem with them?
Well, a few things. As speeds increased, you ran into big problems with signal skew, basically, bits arriving at slightly different times on different wires. That really capped the speed.
Okay, skew. Makes sense.
Plus, you needed loads of pins, which meant complex connectors, bigger chips, and hitting higher bandwidths just got really inefficient. Parallel was hitting a wall.
So PCIe went serial. And point-to-point you mentioned. How did that help?
That point-to-point topology is key. Instead of everyone sharing the same bus, like a crowded highway, each PCIe device gets its own dedicated direct link to the root complex or switch.
Like its own private lane.
Exactly. Dedicated bandwidth. That means your graphics card isn't competing with your network card for speed. It boosts performance massively and makes the whole system more scalable. Essential for modern stuff.
Got it. Dedicated lanes. Now, this physical layer, or PHY, where does that sit in the picture?
Okay, think of PCIe like a stack of communication layers. The PHY is right at the bottom, the foundation. It's the bit that actually interfaces with the physical medium, the copper traces on the motherboard, the connectors, the cables.
So the hardware interface.
Yeah.
But it does more than just connect wires.
Right. Way more. The PHY's job list is pretty long. It has to establish the physical connection, obviously, and keep it running. It takes the digital data from above, serializes it into that high-speed bit stream, and sends it out.
And receives it too, presumably.
Yep. Receives the incoming stream, deserializes it back to parallel data, but it also manages the clocking, figuring out the timing from the data itself. It handles data recovery, deals with noise, basically ensures signal integrity.
Signal integrity, keeping the signal clean.
Right. And it even manages the whole initial setup, the handshake that's link training and initialization. It's a real workhorse, making sure the bits get across reliably.
Okay, a lot going on down there. And the sources mentioned PAPE, PHY interface for PCI Express. What's that about?
PCIe is basically a standard agreement, a defined interface between the mostly analog PHY and the digital world above it, specifically the AMA media access control, part of the data link layer.
A standard handshake point.
Exactly. Intel originally defined it, but it got widely adopted. It creates this clean separation. So chip makers can design PHYs, others can design MS, and as long as they both speak PCIe, they can work together. It allows for modularity, interoperability, super important.
Like a standard USB plug, but for inside the chips. Makes sense. Okay, Gen 1 and Gen 2. We're talking 2.5 GTs and 5.0 GTs. What's GTs?
Gigatransfers per second. Key thing here. It's the raw signaling rate per lane. It counts the encoded bits zipping across the wire before you account for overhead, like the 8B, 10B encoding we'll get into.
So 2.5 billion encoded bits per second per lane for Gen 1, and double that for Gen 2.
That's the raw speed, yeah. Billions of transfers. It's fast.
And Gen 2 was backward compatible. Why was that important?
Oh, massively important for adoption. You could plug a new Gen 2 card into an older Gen 1 slot or vice versa, and it would just work, albeit at the slower Gen 1 speed. You didn't have to upgrade everything at once.
Smooths the transition.
Right. And interestingly, while PCIe 2.0 supported 5.0 GTs, it wasn't actually mandatory for compliance. Running at 2.5 GTs was enough to be called PCIe 2.0 compliant. The 5.0 was the potential.
Okay. Now, you mentioned some key logical functions, SERDAs, 8B, 10B, scrambling. Let's unpack those. They sound crucial.
They absolutely are. These are the core engines inside the PHY making it all work. SERDA's deserializer bridges the parallel chip world and the serial wire world. 8B10B encoding is vital for signal quality and control.
Scrambling.
Yeah.
Sounds like mixing things up.
Yep. Reduces electrical noise, essentially. Then you have byte striping and disque for when you use multiple lanes together, and ordered sets, which are like the PHY's own private command language.
Lots to cover there. Okay, let's start with the connection itself. Links and lanes, what's the difference?
Okay, a link is the whole connection between 2 points, say your CPU's root complex and your graphics card endpoint.
The entire pathway.
Right, and that link is made up of one or more lanes. A lane is the basic building block. It's a pair of differential signal pairs, one for transmitting, TX, one for receiving, RX. So each lane is full duplex, data flows both ways at once.
TX and RX pairs, differential signaling,
Yeah.
and multiple lanes make a wider link.
Exactly. PCIe scales. You can have by 1 lane, by 2, by 4, by 8, by 16, even by 32 in some rare cases. More lanes mean more potential bandwidth.
And how does it decide how many lanes to use?
That's negotiated automatically during link training. The two devices figure out the widest link. They both support and agree on that. So a simple network card might use by 1, but a big GPU needs that by 16 fire hose.
Tailoring bandwidth to the device. Smart.
Right.
Okay, differential signaling. Using 2 wires, D plus and D instead of 1. Why is that so critical?
It's fundamental for high speed. Instead of measuring voltage against ground, the receiver looks at the difference between D plus and D. Big advantage number 1, noise immunity.
How does that work?
External noise tends to hit both wires similarly. That's common mode noise. Since the receiver only cares about the difference, that common noise gets canceled out. Huge deal for reliability.
Like noise-canceling headphones, but for data signals.
Kinda, yeah. Second big win, reduced EMI electromagnetic interference. The opposing signals create fields that mostly cancel each other out, so the link radiates less noise. Good for regulations, good for not messing up other components.
Okay, less noise interference. Any other benefits?
Lower voltage swings. You don't need as big a voltage difference compared to single-ended, which means less power consumption and, crucially, it allows for faster switching, higher data rates.
Lower power, less noise, faster speeds. Sounds ideal. But signal integrity is still a challenge. What about de-emphasis?
Right, even with differential signaling, getting those signals across perfectly at billions of bits per second is hard. The traces on the board, connectors, they act like filters, weakening the high-frequency parts of the signal.
Which you need for sharp transitions between zeros and ones.
Exactly. Weak, high frequencies can cause bits to smear into each other. That's intersymbol interference, or ISI. De-emphasis or pre-emphasis is a trick the transmitter uses.
How does it work?
If it's sending a run of identical bits, say several ones in a row, it slightly reduces the voltage level after the first bit. This makes the eventual transition away from that level seem sharper to the receiver, helping counteract the channel's filtering effect.
So it's actively shaping the signal before sending it.
Yes. It's a basic form of equalization present even in Gen 1, Gen 2, ensuring that signal quality right at the start is a core PHY task before any digital magic happens.
Okay, shaping the signal. Let's peek inside the PHY now. The transmit path data going out. What are the steps?
All right, transmit path. Data comes down from the MACDL, usually via that PCIe interface. If it's a multi-lane link, first step is often byte striping, dealing the data out across the lanes.
Okay, distribute the data.
Then, if it's actual packet data, it hits the scrambler to randomize the patterns. After that, the 8B 10B encoder converts each 8-bit byte or K symbol into its 10-bit counterpart.
8 bits become 10 bits.
Yep. Then that parallel 10-bit symbol goes into the serializer part of the sorties, which turns it into a super fast serial stream for that lane. Finally, the differential driver, maybe with de-emphasis, sends it onto the wire.
Parallel in, stripe, scramble, encode, serialize, drive out. Got it. What about the receive path? Sounds trickier.
It is, generally. Incoming signal hits the differential receiver. First critical job. Clock data recovery, CDR the other half of SerDes. It has to figure out the timing from the noisy, possibly degraded incoming data itself.
Pulling the clock out of the data stream? Wow.
Yeah, it's clever stuff, often using PLLs. Once the clock is recovered, the deserializer uses it to convert the serial stream back into parallel 10-bit symbols.
Okay, back to parallel. What's next?
If it's multi-lane, you've got lane-to-lane skew. So disque logic and elastic buffers kick in. They align the symbols arriving from different lanes and also absorb tiny clock frequency differences between the sender and receiver.
Ah, handling the timing variations.
Right. Once aligned, the 10-bit symbols go to the 8B10B decoder. This reverses the encoding, turning them back into 8-bit data or K symbols, and it checks for errors.
Error checking happens here too.
Basic checks, yeah. Then, if it was scrambled, the descrambler undoes that using a synchronized sequence generator. And finally, if multi-lane, byte unstriping reassembles the bytes in order before sending the parallel data back up via PCIe.
So receive is recover flock data, deserialize, deskew buffer, decoder check, descramble, unstripe, send up. Much more involved.
Definitely. The receive side deals with all the imperfections of the real-world channel. It's where a lot of the analog and digital magic happens. The PHY is that crucial analog-digital bridge.
Okay, let's zoom in on SerDes, serializer to serializer. You said it bridges parallel and serial. How essential is it?
Absolutely fundamental. Chips think in parallel wide buses inside, but sending that wide bus directly at gigahertz speeds is impractical. SerDes is the translator.
That's so.
The serializer takes those relatively slower, wider parallel paths, like the 10-bit symbols from the encoder, and funnels them into a single, extremely fast serial stream suitable for the external link.
And the deserializer does the reverse.
Exactly. Takes that incoming ultra-fast serial stream and converts it back into a wider parallel format that the rest of the chip logic can handle at more manageable speeds. It's the speed bottleneck converter, essentially.
Makes sense. And clock data recovery, CDR, is part of the deserializer's job. Why recover the clock from the data? Why not send a separate clock signal?
Sending a separate clock reliably at these speeds alongside the data introduces its own massive problems, mainly skew between the clock and data. Embedding the clock in the data avoids that.
How is it embedded?
The CDR circuit looks for the transitions in the data at the edges where it goes from 0 to 1 or 1 to 0. By constantly tracking the timing of these transitions using clever circuits like phase-locked loops, PLLs, it can reconstruct a clock signal that's locked to the incoming data rate.
So it needs frequent transitions to work reliably.
Absolutely. If the data stayed flat, all zeros or all ones for too long, the CDR might lose lock. That's a key reason for using 8B10B. Encoding it guarantees a minimum number of transitions within any given stretch of data.
So 8B10B helps keep the CDR locked. Clever. You also mentioned the link is asynchronous. What does that mean?
It means the device at one end, transmitter, and the device at the other end, receiver, are each running off their own independent clock sources, their own crystals. They aren't sharing a common clock.
But their clocks won't be exactly the same speed, right?
Precisely. There's always a small tolerance, maybe 300 parts per million for Gen1, Gen2. Seems tiny, but over millions of bits, the receiver might start drifting relative to the transmitter.
How is that handled?
That's where those elastic buffers on the receive side come in, along with special symbols called SKP symbols, bundled into skip-ordered sets. The buffer can stretch or shrink slightly, and SKP symbols can be added or removed as needed to prevent the buffer from overflowing or running empty due to these slight clock differences.
Wow, dynamic adjustments on the fly. Okay, let's dive deep into 8B10B encoding now, turning 8 bits into 10. What are all the benefits?
Okay, 8B10B does several critical things. First, as we said, it guarantees frequent transitions, which is essential for reliable clock data recovery. Second, it ensures DC balance.
DC balance, why does that matter?
High-speed links are often AC coupled, meaning they block constant DC voltage. If you sent too many ones or zeros in a row, you'd build up a DC bias that could mess up the signal levels. 8B10B encoding carefully chooses the 10-bit codes to keep the number of ones and zeros roughly equal over time, preventing this DC buildup.
Keeps the signal centered, electrically speaking.
Exactly. Third, it provides some basic error detection. Not all 124 possible 10-bit patterns are valid codes. If the receiver sees an invalid pattern, it knows an error likely occurred.
A built-in sanity check.
Kind of. And fourth, it allows for those special K symbols or control characters. These are distinct 10-bit patterns used for signaling within the physical layer itself without messing up the actual data path. Things like marking packet boundaries, link management signals, etc.
In-band signaling using special codes. How does the encoding actually work? Looks complicated.
It's clever. It splits the 8-bit input into a 5-bit group and a 3-bit group. Each group is encoded separately using predefined lookup tables into a 6-bit and a 4-bit pattern, respectively. These are then combined to form the 10-bit symbol.
Okay, lookup tables. But how does it maintain the DC balance?
That involves something called running disparity, RD. The encoder keeps track of whether it has sent more ones than zeros, positive RD, or more zeros than ones, negative RD, so far. For many 8-bit inputs, there are actually two possible 10-bit encodings, one that adds more ones and one that adds more zeros.
So it chooses the one that helps balance things out.
Precisely. Based on the current running disparity, it picks the 10-bit code that will push the disparity back towards 0 or keep it balanced. The receiver tracks this RD too, which also helps with error detection.
Fascinating. And these K symbols, you mentioned COM, SKP, IDL.
Right. There are 256 possible 8-bit data values, which map to D symbols. But the encoding scheme also defines 12 special K symbols. K28.5 key M is crucial for symbol alignment and marks the start of ordered sets.
Comma for alignment. Got it.
K28.0 SKP is used in the skip ordered set for that clock tolerance compensation. K27.7 IDL signals entry into electrical idle for low power states. K28.3 FTS is for fast recovery from low power. Others, STP, END, etc., are used more by the data link layer for packet framing.
So the PHY uses these K symbols, often in specific sequences called ordered sets, for its own control messages.
Exactly, and the interface, like PIPE, distinguishes between D and K symbols, so the layers know what's data and what's control.
What about decoding and error checking on the receiver side?
The receiver does the reverse lookup. It checks if the incoming 10-bit symbol is a valid D or K code. If not, that's a code error. It also tracks the running disparity. If a received symbol's disparity doesn't match what's expected based on the tracked RD, that's a disparity error.
But it flags those errors.
Yeah, it reports them up the stack. But importantly, 8B10B error detection isn't perfect. 2 errors could potentially flip a valid code into another valid plane. That's why you still need stronger checks like CRCs at the data link layer.
First line of defense, not the whole army. Okay, the big elephant in the room.
Yeah.
25% overhead. 10 bits for 8 bits of data. That's significant.
It is. It means your effective data rate is only 80% of the raw signaling rate. So Gen 1 at 2.0 grabs of actual data per lane, Gen 2 at 5.0 GTs gives 4.0 grabs per lane.
Was that overhead worth it?
Back then, absolutely. The benefits guarantee transitions for CDR, DC balance for signal integrity, K symbols for control, basic error checking were deemed essential for making reliable high-speed serial links work at all. It was a necessary trade-off.
A trade-off they later improved on with 128B, 130B encoding in Gen 3 and beyond.
Exactly. More efficient, but also required more sophisticated equalization techniques because it didn't have the same inherent DC balance and transition density guarantees as 8B10B.
Interesting evolution. Okay, next up, scrambling. Happens before 8B10B on transmit, after on receive. Why scramble if 8B10B already helps with transitions and balance?
Scrambling serves a couple of key purposes. The big one is reducing EMI. Repetitive data patterns, even after 8B10B encoding, can create strong peaks in the signal's frequency spectrum, leading to unwanted radio emissions.
Like broadcasting on a specific channel.
Sort of. Scrambling uses a pseudo-random sequence to break up those patterns, spreading the signal energy more evenly across a wider frequency range. Think of it like adding white noise to smooth things out. Less EMI, easier compliance.
Okay, smoother spectrum, less noise. What else?
It also enhances signal randomness generally. While 8B10D limits short runs of identical bits, scrambling helps break up longer-range repetitive patterns that might still challenge clock recovery or equalization circuits. It adds another layer of robustness.
How does it actually work? You mentioned LFSRs.
Yeah, a linear feedback shift register. It's a digital circuit that generates a long, predictable, but seemingly random sequence of bits, a pseudo-random binary sequence, PRBS.
Predictable, but random.
Predictable if you know the starting state and the polynomial defining the feedback taps. But the sequence looks random statistically.
Okay. So how is it used?
On the transmit side, each 8-bit data byte before 8B10B is XR'd with the 8 bits currently coming out of the LFSR. This scrambles the data.
XRing with a pseudo-random sequence.
Right. The receiver has an identical LFSR running the same polynomial. Crucially, it needs to be synchronized with the transmitter's LFSR. After 8B10B decoding, the receiver XORs the incoming 8-bit data byte with the output of its own synchronized LFSR.
And XRing twice with the same value gets you back the original.
Exactly. Data XOR PRBS, XOR PRBS data. The scrambling is reversed.
Clever. What's the polynomial for Gen 1, Gen 2?
It's a 16-bit LFSR defined by GX plus XO plus XOR plus XOR plus 1. That specific formula dictates how the sequence is generated.
And how do they stay synchronized? That sounds critical.
It is. Synchronization happens using the COM, K28.5 symbol. Whenever a transmitter sends a COM or a receiver sees one, they both reset their LFSRs to a known starting state all once, FFFF hex.
So COM acts as a resync point for the scrambler too.
Yes. Since comms appear frequently, especially at the start of ordered sets, it keeps the scramblers locked together.
Does everything get scrambled?
No. Scrambling is only applied to data symbols, decodes, within TLPs and DLLPs. It's disabled for all special symbols, K-codes, all ordered sets, and certain test patterns. The PHY needs to see those K symbols and ordered sets unscrambled to interpret them correctly.
Makes sense. And you mentioned a quirk with SKP symbols.
Right. Normally, the LFSR keeps advancing even when scrambling is off, but when an SKP symbol is being processed, transmitted, or received, the LFSR state is held constant. It doesn't advance.
Why that exception?
Because the receiver might add or delete SKP symbols for clock tolerance. If the LFSR kept advancing during a deleted SKP, the receiver's LFSR would get out of sync with the transmitters. Holding it steady during SKP processing ensures they stay aligned even if the SKP count changes slightly.
Another subtle detail for robustness. Okay, multi-lane operation. Combining lanes for more speed. How does byte striping work?
It's pretty straightforward conceptually. Let's say you have a by-4 link. The PHY takes the stream of 10-bit symbols after encoding and deals them out, round-robin, across the 4 lanes. Symbol 1 to lane 0, symbol 2 to lane 1, symbol 3 to lane 2, symbol 4 to lane 3, symbol 5 back to lane 0, and so on.
Symbol striping, really, since it's post-encoding.
Technically, yes. Byte striping is the common term, but it happens at the symbol level here. The goal is simple. Multiply the bandwidth. A by-4 link sends 4 symbols simultaneously compared to a by-1 link's 1 symbol, giving roughly 4x the throughput.
Seems simple enough. But what about lane-to-lane skew? The symbols won't arrive at exactly the same time, right?
Correct. Tiny differences in trace lengths on the PCB, variations in chip circuitry. It all adds up to slight differences in arrival time for corresponding symbols on different lanes. That's lane-to-lane skew.
How does the receiver handle that? It needs to put the symbols back together in the right order.
It uses a deskew mechanism. Each receive lane typically has a small elastic buffer. During link training, special sequences, like parts of TS1, TS2 ordered sets, are sent. The receiver measures the arrival time of these known patterns on each lane.
Measures the skew between lanes.
Yes, it figures out which lane is the slowest. Then it uses the buffers on the faster lanes to delay their symbols just enough to align them perfectly with the symbols arriving on the slowest lane.
Holding back the faster runner so everyone finishes together.
Exactly. Once all the corresponding symbols for a given time slice are aligned in the buffers, the byte unstriking logic can read them out in the correct interleaved order, lane 0, lane 1, lane 2, and reconstruct the original symbol stream.
So deskewing is vital for multi-lane. Relies on buffers, training sequences, lots of coordination.
Absolutely. It ties together SERDAs, CDR, link training logic, buffer management. It's a complex dance to make multi-lane links reliable.
Okay, last major piece. Ordered sets. The PHY's private language. What's their overall job?
Ordered sets are specific sequences of 10B symbols, mostly K symbols, used exclusively by the PHYs at each end of the link to talk to each other and manage the link state. They're separate from the TLPs and DLLPs carrying data and higher-level control.
What kind of management tasks?
All sorts. Link training, negotiating speed, width, lane numbers, navigating the link training and status state machine, LTSSM, handling clock tolerance compensation, the SKPOS, managing power state transitions like entering electrical idle, using EIOS, even configuring lane polarity if needed.
So the control panel for the physical link itself.
Pretty much. They nearly always start with COM, K28.5, for easy detection and synchronization, are sent simultaneously on all active lanes, and crucially, they are not scrambled.
Unscrambled commands. Can we quickly recap the key ones for Gen1, Gen2, TS1, TS2?
Right. TS1 and TS2 are the workhorses of linked training, 16 symbols long, starting with COM. They carry bits that signal capabilities, negotiate speed width, assign link lane numbers, request speed changes, indicate equalization readiness, less critical in Gen 12, and determine the NFTS value for L0's recovery. The whole LTSSM progression depends on exchanging these.
Okay, the training negotiators. SKPOS.
Skip ordered set, just 4 symbols. COM plus 3x SKP, K28.0, used for clock tolerance. Receiver periodically inserts these and can delete SKPs from the stream to keep its elastic buffer from over underflowing due to clock drift, usually sent every 1200, 1500 symbol times or so.
The clock drift manager.
EIOS.
Electrical idle ordered set, COM plus 3x IDL, K27.7, sent just before a device wants to enter a low power state like L1 by putting the link into electrical idle, stopping transmission. It's the going quiet now signal.
And FTS-OS. Fast training sequence, TextCom, plus NFTS-X, FTS, K28.3, plus N symbol. NFTS is negotiated via TS1, TS2. FTS-OS allows a very fast recovery from the L0's low power state back to the fully active L0 state. Lets the receiver quickly resync bit symbol lock without a full retrain, saves time and power.
So TS for training, SKP for clock drift, EIOS for idle entry, FTS for fast wake up, a tool for every job.
Exactly. They provide the essential control fabric for the physical layer.
Okay, that's a lot of intricate pieces.
Yeah.
Can we do one final quick summary walkthrough? Transmit path first?
Sure, transmit. Data comes down via PCIe, maybe byte striped across lanes, scrambled. If data in TLP-DLLP, legacy 8B10B encoded, tracking RD, serialized by SerDes driven differentially, maybe with de-emphasis.
Got it. And receive?
Receive. Differential signal comes in, CDR recovers clock data, deserialized by SerDes lane to skew and elastic buffering, aligns lanes, handles clock drift domain crossing, 908B10B decoded, checking errors, tracking RD, track is scrambled if needed, byte unstriped, reassembles lanes, data goes up via PCIe.
It really highlights how much more complex the receive side is, dealing with the channel imperfections.
Absolutely. Clock recovery, data recovery, skew compensation, clock tolerance, error checking. It's where the analog meets the digital under challenging conditions. Sophisticated stuff.
Absolutely fascinating. So wrapping up this deep dive, what are the biggest takeaways about the Gen 1, Gen 2 PHY?
I think it's the combination of clever techniques working together, SerDes for the speed conversion, CDR needing those transitions, 8B10B providing transitions, DC balance and control symbols, scrambling for EMI and randomness, multi-lane striping to skew for bandwidth scaling, and ordered sets as the PHY's own control channel.
A layered set of solutions.
Exactly. Even though speeds and encoding have advanced massively since then, these foundational concepts dealing with timing, noise, synchronization, and coding overhead, they really set the stage. Gen 1 and Gen 2 PHY solved fundamental problems in high-speed serial communication.
Incredible groundwork. It's easy to forget all this complexity is humming away inside our machines constantly. So a final thought for our listeners.
Yeah, maybe think about this. We've seen the challenges faced in Gen 2, timing, noise, sync. How do you think today's cutting-edge interconnects, pushing hundreds of gigabits or even terabits per second, are tackling even more extreme versions of these same fundamental problems? What echoes of this early PCIe PHY might still exist in, say, PCIe Gen 6 or future technologies? Something to ponder.
A great question to chew on. Well, thanks for joining us on the Deep Dive.